Welcome back to ECE 441A 541A. This is our last meeting of the semester as a class. The next time will be as a final exam. It seems like it's gone by very fast. I just recall it seems like a week ago that we were starting in this environment, although I think we've lost a few bodies. I don't know where they are, but anyway, hopefully they will be here by the final exam. Today you have a lot due, especially I guess if you're in the 541 section of the class. You have homeworks 9 and 10 for everyone, lab number 3 for everyone, and project for 541A is due today. In addition, the teacher course evaluations are due, and hopefully that link would work. If you haven't received the link many times, I don't know how frequently you are updated with that information, but please fill that out if you can squeeze it in. It's useful information. It is anonymous, and I don't see them or don't have access to them until after, obviously, grades have been posted a long time in the past. Final exam is next week on Tuesday at 10:30 a.m. It is a Tuesday, so make sure that you're okay with that in your schedule. Office hours prior to the final, the only one that's normal, that's consistent with what we've been having all semester, is today's office hour from 12:30 to 2:30. The others have had to be adjusted for scheduling purposes, and I introduced a Monday office hour when I'm available, which is late in the day. Maybe that's better for you. But at 4 o'clock on Monday, I will be in 523 for office hours, if that helps. But note that Thursdays and Fridays are different from the normal times. Thursdays have been slid an hour, as have Fridays. Those have all been moved to a later time in the day by 1 hour. But those are the office hours. If you would like to ask questions during that time before the final exam. Again, our final exam is on Tuesday from 10:30 to 12:30, and it will be in this room. And hopefully we will fill the room by that date. Today what I want to do is go over the process for the final, which is consistent with what we've done in previous exams, except you will get one more page, which is front and back of notes. The material for the final exam, actually I gave you on day 1. That's on page 6 of the syllabus in terms of outcomes or learning tasks that you need to be able to do by the end of the semester, and I think that's on page 6 of the syllabus. Then we will pull out some of the tables from the textbook, and the first one will sort of be addressing which controller type do you pull out of your toolkit. Do you use a phase lead? Do you use a phase lag? And that's documented or discussed in Table 6 of Chapter 10. Then I'll show you some realizations, meaning how would you physically build these controllers, these G sub C of S's that we've been talking about. That's in the book. It was way back in one of our first homework problems where you actually had to find the partial fraction expansion of a transfer function, and you're going, this looks like a crazy partial fraction expansion. It was actually a PID controller or a phase lead, phase lag controller, and I think that's what figure AP 2.9 will illustrate. We'll go ahead and recap what we've done in the last time, but if there are questions that you would prefer get answered today, I'm open to that, and you can just read on your own this comparison of output feedback control, designing a cascade G sub C of S versus full state feedback. And you'll be required to do all of that on the final. You won't necessarily be comparing and contrasting on the final. You will just be producing a G sub C or several G sub C of S's and a full state feedback controller design. And I wouldn't want to leave you without a little bit additional information, and that is, how can we incorporate integral control into this full state feedback mechanism or strategy that we've been doing so far this semester. The full state feedback seemed to be nice, but if there were errors or uncertainty in the A matrix, the B matrix, and the C matrix, we might be quite off if we were trying to track a reference input with our output. And that integrator was sure nice. That integrator sitting in the earlier output feedback control, that integrated the error away and allowed our output to track our reference in a constant scenario without error after the transients. And so I'll quickly draw you the block diagram, and now with all of your skills, you can now label that diagram up, find a state space representation, and really it is or converts itself into a full state feedback controller design in an augmented system environment. Augmented meaning you have your A matrix, your system matrix, but you augment that with its additional dynamics due to the integrator. And that really is introducing another pole at the origin in this augmented state space representation. Let me pause while everybody takes a drink or a deep breath, but the final will be comprehensive, and it's 15 questions. It's designed to challenge you maybe, but not discourage you. But some people don't get discouraged. It's 15 questions. Be prepared. And you do have your 4 sheets of notes as your comfort. You can also bring in a copy that you provide of the Laplace transform tables, table 2.3. And I hope you don't say with your hand in the air, can I borrow somebody's table? Sorry, no, I won't be able to do that. Or if we have another proctor here, I think the vote was you liked the other proctoring on exam 3. All right, well, I will try to be here on the final. You can have a calculator. You can bring a protractor, but there are some no-nos. No computer, no cell phone, no textbook, no course notes beyond the 4 pages that you bring, and most of you can write and see quite small font, so apparently you can condense an entire semester on 8 pages of material, which is what you have. Good for you, as long as you can interpret it. The topics, as I said, here is page 6. I'm not going to read through those. The exam, the final, is 15 questions. You're already doing the math. There's 17 outcomes. I might throw out a couple of these, but I don't think I'm going to necessarily introduce anything new. But these are a little bit general in terms of what they state, but you should be able to perform well on the final exam if you're prepared to go forwards and backwards with these kinds of learning outcomes. The other thing that you can do is, after looking at these and saying, oh, I need to brush up on this, I need to brush up on that, you can go back and look at the more detailed topic lists for exam 1, 2, 3, and I also produced another one post exam number 3, and that I think is in the final exam module on D2L. So I do have an additional list. I don't remember how many items are on that, maybe 20, but that's sub exam number 3 to sort of fine-tune or get into a little bit more detail what is covered in this very concise form of the topics for the class. Questions on the final exam? Yes. Will I be posting any practice finals? Oh, I should have anticipated that question. I don't think so. So now what you'll need to do, I have posted practice exams from 1, 2, and 3, and I have introduced or posted an old exam 3 problem or problems in the final exam module, and that deals with Bodie plot material, which is what we're doing post exam 3. And you should be very comfortable with homeworks 8 and 9, which deal with the Bodie plot material for the final. So it's about the same. It's just you have now 15 problems instead of, although the third exam is kind of getting you close to the final in terms of number of questions. I think it was 9. And I have a fun time grading 15 problems from the but that's my problem, not yours. You make it my problem and do a good job. Other questions on the final? Again, I'm not going to read through this table, but you have it or will have it in your notes. It's table 10.6. It summarizes phase lead and phase lag controllers, or compensation or compensators, and it sort of says what's the approach, what are some advantages and disadvantages, maybe some applications, when or what situations might this not be applicable. That's now compared and contrasted in this 2-column format in table 10.6. And if you've been able to take notes on that in this amount of time, I am very impressed. But here are some possible realizations or ways to implement the various controllers that we've been building on paper and pencil, G sub C of S's. These are now just made from a couple of op-amps. And you can now build a PD controller, a PI controller, and obviously this lead or lag. And then if you put them together, which is sort of the next piece, you can have a phase lead, phase lag controller. But when somebody says, here's a collection of zero and pole factors, this is maybe what you can think about in terms of how would I actually build that, or where is this coming from? Now granted, you probably will have to enhance by meaning make the system have a little bit more power to push into whatever you're driving. If you're now driving a huge motor and you have this wimpy little op-amp sitting there and maybe some other 9-volt battery supplying it, you may run into trouble. So you may have to have some power transistors, some power amplifiers incorporated, but here is sort of assuming that all the impedances and all the relationships, all the loading don't necessarily matter too much. Here's the PID controller that I had referred to before. And this one is done with a series combination of R and C and a parallel combination, with the series in the feedback path and the parallel in the input path of this single op-amp circuit. Obviously it's inverting, so if you want to now change the sign, you could build a inverting op-amp circuit and attach it to this. And now you have the PID controller that we've been playing with all semester. Questions? In general, before we move on to a controller comparison, which is really sort of a summary of what we've done in the last lecture. So I'm open for questions if you have questions. Homework questions. Did you find that one of those, is everybody finished with their homework? You now have homeworks 9 and 10 that you will be submitting, done or not, into the Dropbox. But homework, I believe 9, maybe the last problem was a phase lead controller design. I had several students come in and say, I'm kind of pulling my hair out on this one. What's up with this recipe? It's not seeming to work. Well, the recipe is just that. You might have to do a little bit more shaking and baking to make some of these controller designs work. In this case, you had a pole at the origin, a pole at -1, and a pole at -2. Those are pretty well on top of each other, the -1 and -2, and so you're rolling off in magnitude and phase quite a bit at crossover. And a single first order factor of a 0 and a pole may be a challenge to bring that up to speed, or to meet your design specifications. And if you look at the root locus, you're going to say, wait, even if I can cancel that pole at -1, I'm never going to get the settling time spec because I'm always going to be a little bit to the right of s equal -1 for my real part on the pole, on the closed loop poles. Granted, if you put in another factor, another phase lead factor, and canceled that pole at -2, now you kind of put in a couple of poles over further into the left, and it's probably pretty straightforward. If you fix, or if you restrict yourself to just a first order compensator, then okay, let's just say your phase lead, the recipe got me pretty close with my 0 to canceling that pole at -1. I hope this isn't just all hot air that I'm saying. I hope you've played with the problem a little bit. Well, if it was at 0.8, what about just moving it all the way to s equal -1 and canceling that pole? And now throw a pole in somewhere over into the left half plane to try to get the phase margin specification met. And then the settling time, you know, is not going to be quite 4 seconds. But if it's close, that's good enough for this class. So those kinds of decisions on the recipe, if I'm calling it a recipe, maybe that gives you a clue that with a little experience, a little bit of time in the kitchen, you get better at cooking with this recipe or these recipes. Just saying, there might be a reality show coming later about, you know, controller recipes. I'm sure it would have a large following if such a reality show were on the airways or even on the internet. It already exists, doesn't it? We've got a YouTube channel. Anyway, controller comparison or questions. Here's a state space representation. It's very familiar, and this one, where are the poles of this? Well, duh. If you haven't looked up yet, where are the poles of this system? Can you tell me without mentally computing the transfer function by just looking at these system matrices? And in particular, you're looking at the system matrix, which is the A matrix. The eigenvalues of A tell you your closed, or tell you the poles of this system, and they are the open loop poles in this case. And with a little ECE 310 or a math linear algebra, you know that since this is upper triangular, or if it was lower triangular, this one's upper triangular, your eigenvalues of that system matrix A are on the diagonal. Wow, I see a 0 and I see a -1. My poles are at 0 and -1. That's now the state space representation. You could do your cheer. C times SI minus A inverse B to compute the transfer function. Maybe some of you just enjoy drawing all integrator block diagrams. You could do that with this system matrix, or these state space matrix representations, and actually compute the transfer function using Mason's gain or using block diagram algebra. And you should obtain the same G of S. Or I could give you a Bode plot. Do you see the Bode plot for this system? Where does the phase begin at low frequencies for this system's Bode plot? Does it start at 0 degrees? Does it start at plus 90? Does it start at minus 90? I could even make the final multiple choice, couldn't I? Maybe. Everyone's favorite. Multiple choice exams. Just saying, it might make my job easier on grading. So I'm getting some ideas as I'm talking today. Or just having a conversation. Where's my phase starting at low frequencies? Pardon? Minus 90, because of that pull at the origin. Where is it finishing? At high frequencies, what's my phase? And what influences that? Here, this is too easy of a transfer function to test that in general. But in general, you're looking at the pole zero excess, aren't you? How many more poles do I have than zeros? That will influence my net angle at high frequencies. Here I don't have any finite zeros, so there's no angles that they're contributing. I'm just having two poles. Those poles, linear factors, contribute 90 degrees each, so I'm living or at high frequencies at minus 180 degrees. What's my gain margin for this system? What determines the gain margin? If I'm after gain margin, which plot am I using to find the frequency of interest? The magnitude plot or the phase plot? That's maybe kind of a weird question to ask, but what determines the frequency at which my phase margin is, or I'm sorry, my gain margin is determined? It's the phase crossover frequency, and does this ever cross minus 180 degrees? No, so theoretically the gain margin on this system is infinite. If you drew the root locus of this system, you crank up the gain, you just keep cranking up the gain, you're never going to go unstable. You will go quite oscillatory. You will have quite an overshoot, but you have an infinite gain margin. There's the system in different forms, one in block diagram form, one as an all-integrator block diagram, and you should be able to connect those two forms. How could you convert one into the other? Can you go from the transfer function into a state space representation? That's a final exam possible question. If I just gave you the top block diagram, can you now create a state space representation for that block diagram or associated with that system? Do you remember how to do that? If you don't, that's something you might want to play with between now and the final. How do you find the state space representation for the bottom figure? Now you are playing with me because we talked about this last time, right? You assign or label the outputs of the integrators as your state variables. So you have two states and it's not unique. If you wanted the transfer function, you could convert those or just move into the frequency domain with this block diagram and convert those integrals into 1 over s operations and find the transfer function from the bottom equation or diagram. This is going to be a fun day. I've already fallen up the stairs. What else can I do in getting here? Need to pick up my... Okay, so design specifications. 3 specs: steady state error or steady state accuracy, settling time, and percent overshoot. And I've listed in these clouds, we have a purple cloud or magenta and a green cloud, some properties of particular types of system. If I have a type 0 system, what is that referring to? You don't have any poles at the origin, do you? And typically we focus on these systems as, in fact, the combination of our G sub C and G. That cascade or series combination is what influences. Actually, let me make a change. Since you are already way ahead of me and probably already copied this down, but there's the definition of the velocity gain constant in a type 1 system. A type 1 system is where you have one pole at the origin, and there, what's the steady state error due to a constant? If we have a type 1 system and we control it with a cascade compensator, what's the steady state error due to a constant input? Because it's type 1, we have 0 error due to constant inputs, reference inputs. Here's the block diagram that we're using to discuss these different system types and these expressions if you're now trying to find the steady state error under different scenarios, where you can find either the transfer function between R and Y or the transfer function between R and E. And they're obviously not the same. And on the final, you might be asked to find either or both of those. Or if you're asked to find the steady state error, you should be able to do that based on what you now know or have available in your skill set. If we're going to control this system, we need to first figure out where we want to go. We have open loop poles at 0 and -1. We can translate those last two design specifications into transient, or those are transient based design specs. We can translate those into closed loop system poles. A settling time of 1 second says that we need a real part at 4 or bigger, moving further into the left half plane. The percent overshoot specification of 5%, you could quickly look at figure 5.7 and eyeball that, or 5%, we just agree that's 45 degrees in terms of its angle. Or if you really like to feel warm and fuzzy with pushing numbers on your calculator and doing all the math, you can use those percent overshoot and zeta expressions. If you use the zeta expression, don't forget to take the square root of that ratio. With a 5% overshoot and a settling time of 1 second, we now have desired closed loop poles at -4 plus and minus J4. You could find the peak time from omega sub d if you wanted it, which wasn't a design spec. But now we could also convert that into a desired polynomial for our full state feedback controller design, where each factor now is determined by one of those complex conjugate poles. S minus the pole in the second quadrant, S minus the pole in the third quadrant. And minus a minus gives us that S plus 4. And we now have S plus 4 minus J4 and S plus 4 plus J4. Those are conjugate pairs, and we end up with a polynomial that has real coefficients. In this class, we're focusing on cascade compensators with output feedback, this block diagram, and full state feedback strategies. Here you could have different questions concerning different points of interest. If you're interested in the steady state error, you might need to know what is E of S, or what happens to E in the steady state. Full state feedback. Now hopefully you can compare that with the output feedback, and you can see that it's a fair amount different. Now we are really messing up the fact that we started with a pole at the origin. Now we've eliminated that by the feedback of minus K1. And we use N to establish our DC gain level. Now I just want to see if you were paying attention the last time we were together. Here's an S-plane plot, or coordinate. I'll plot the poles and zeros of the system. And now you can suggest what you would do for G sub C to actually achieve the desired pole locations, which were at -4 plus and minus J4. You want your root locus branches to go through those triangles, and those will influence your dominant poles. Which says you can already see, and I've already sketched the original root locus with just a gain controller K, and that gave you what kind of a settling time with just a gain controller. What was the real part of your closed loop poles if you cranked up the gain enough? It was -1/2, wasn't it? So now you have sigma is in 1/2. 4 over sigma says you have a settling time of 8 seconds with just a gain controller. That's not close to 1. So you would have to do something other than a gain controller on the final exam to get reasonable credit for your answer. What do we do now? It's usually a good idea to cancel poles or zeros if they're in the left half plane, if that will help. And I hope you remember where never to cancel poles and zeros. I did my best to slap my hand when I was grading exam number 3 when some of you would cancel poles and zeros in the right half plane. I wanted to just give you an E and post the grade, final grade on the grade book. But I kept myself from doing that, since I promised you that was probably what would happen. But don't do that on the final either. It wasn't just the third exam that you have that to abide by. Don't do it in real life either. Don't cancel poles and zeros in the right half plane or on the imaginary axis. They will come back to bite you because you will have a fixed pole at that location. It may not appear if you exactly cancel it between the reference input and the output, but now if you get a disturbance, whoa, that disturbance may excite that mode, and wow, now that disturbance has driven our system unstable. Where do I put my pole? Oh, and we can't just throw zeros down. We can't just have one shaker. If we have a pole shaker and a zero shaker for a purpose, we have to season our S-plane somewhat consistently. If we throw a zero down, we have to throw a pole down. Why? What's the reasoning behind that? You say, I don't like poles, I really like zeros. I like salt, I don't like pepper, or vice versa. No, we have to like both in this class. Why? Why can I not just put a zero down? So what? If you now had to realize that zero, what would it look like? Your G sub C what's that S do in the time domain? And G sub C is taking this error signal and creating an input. Suppose that this error signal was high frequency noise. And what's an S do to that in the time domain? It differentiates it. It makes that look even worse. And now you're exciting your system with something that it does not like. So that's why we're staying away from just a zero, a pure zero. So we won't do that. Somebody has said we already have put that zero there. But the pole now, to roll that off, you can draw the Bode plot of G sub C of S and see that you're not just increasing gain at high frequency if you have that pole there. Hopefully we're okay to put that pole at -8, and that will make our design quite easy. Because now we have exactly the same shape that we had before. They meet halfway, which is -4. And now all I have to do is calculate the gain K, which really is just, if you had your ruler and if you forgot your calculator on the final, which we don't want to have happen, we're seeming to do that more often, not the same people, thankfully, but now we have our ruler and we can measure those two lengths. That's really all we're doing when we calculate that distance from the zero, or the magnitude of S. That's just the hypotenuse from the origin to that triangle. The other piece that we do, in this case, since we placed our other pole at 8, is we have that magnitude, and we didn't have in our plant, we didn't have something here. If we had a 10 there, we would have to divide by that 10. Or if we had a zero factor, S plus Z7, then we would have that down here. But we didn't have that. It was nice and clean. If I can clean this up. We just have that, and now to evaluate that, we're simply measuring those two lengths, or the square root of 4 squared plus 4 squared times that same quantity. That hypotenuse is the same in both pieces, so we really have the argument of those two square roots. Since I'm squaring those two square roots, I have 4 squared plus 4 squared, or 32 for my k. That was pretty straightforward. And what kind of a controller is that? Phase lead or phase lag? That's a phase lead, and you could see that several different ways, but the quickest is just the 0 is closer to the origin than the pole. Full state feedback, we need the system matrix in the closed loop. That's A minus BK. If I give you an A and a B, you need to be able to find the dimensions of K. K has to be compatibly dimensioned to make this formula, A minus BK, work. By that I mean however many columns you have in B, that's how many rows you have in K. And how many columns you have in A, that's how many columns you have in K. In this case, B or K is a 1 by 2 matrix, and we can now plug that in. We now have S here, and we're subtracting a 1. We have subtracting a minus K1, and then we have an S plus 1 plus K sub 2. And now we know what our characteristic polynomial looks like as a function of these unknown or yet to be determined full state feedback gain values, K1 and K2, and we can find those by equating the coefficients of this with our desired polynomial, which was S squared plus 8S plus 32, if I remember right. So now K1 is 32, and K sub 2 is 7. Or we now have minus 32 x1 of t minus 7 x2 of t plus n r of t. And how do we find n? I'll just tell you. Been telling you all morning, right? So now n is found by finding the DC gain of t sub c of s. That's found by setting s equal to 0 in the t sub c of s expression and setting that equal to 1. In our case, did we do that? Well, maybe I didn't. But this will result in n equaling 32. Questions on that? Now I know what you're going to be doing post-final exam. I'm not even going to ask, but here's some information that's beyond the final. So now I've really lost you, haven't I, in terms of your attention. But what if we wanted to guarantee 0 steady state error with full state feedback Because if we now plugged in capital N equal to 32, and we had some errors in our A, B, C, and K matrix, we might not obtain a steady state error of 0. So the way to do that is to introduce an integrator, and here's the block diagram. I know you just love to look at block diagrams. So I'm trying to satisfy that need. Here's a integral control augmented with or onto a full state feedback. In black and blue, our system is all beat up. It's black and blue, but there's the x dot equal ax plus bu, c or y is equal to cx. That's in black. In blue is the full state feedback. We're feeding back x through the full state feedback gain matrix K, and that now gives us our controlled system that we just worked on, except now what we're doing is we're augmenting this entire block with one integrator and scaling the output of that integrator by K sub I, an additional gain. And what do we do with these outputs of the integrators? We assign those as state variables. So now you could have an augmented state vector, x, which might be 10 rows tall, and on the bottom of that is x sub I. And now you have an augmented full state feedback gain matrix problem in the augmented system matrix. If you want to play with this post-final, I encourage you to do it. I know that you'll just probably go home and spend New Year's Eve maybe doing something like that. Is sketching block diagrams, labeling them, finding the augmented system representation, and determining these Ks. Is that okay? Sorry. Just to finish, before class I went ahead and typed up some MATLAB commands to try to give us the responses that we just designed for. Here is the step response with output feedback control, with our phase lead controller. And if this is the right one, I don't know if I can find my mouse. Do I have a mouse? Okay, if I do a mouse, if I right click, I hope you know how to kind of do this. I could actually find my peak response if this keyboard would work. Did I meet my overshoot spec? You have young eyes, can you see that? Somewhere it's up there. 4%, and we were trying to get 5%, so that's pretty good. What's our settling time? We could also right mouse click on our step response plot and say, what are the system characteristics? And say, what's our settling time? And then go up. Let me move this one over if I can. This, obviously my left mouse is not wanting to respond very well, but there's our settling time. Almost 1 second. And who knows, this might be using a 1% settling time MATLAB, and we were working with a 2% settling time, so we're probably fine with our settling time specification. That was the output feedback result. Here's our full state feedback without introducing capital N. And where did we go? We hit this with 1, and where did we settle? What's our final value? Is it 1? This is trying to justify why we need N, capital N. We're way below 1. We're at 0.03, a little bit above 0.03. But if we now put a capital N in there of 32, does that look better? The shape looks the same, This one's scaled now by a factor of 32. Now when we put in a 1, we get a 1 out. Because I've done it, we have to look at these. I also sketched the Bode plot sketched. I had MATLAB sketch the Bode plot, and can you from this diagram see what your gain margin is? What's the phase margin? Is this system stable? Do you see how to answer those questions? Without, well, and in MATLAB you can just cheat and do the margin, and there's the margin. It actually says, oh, your gain margin is infinite, and your phase margin is where your gain crossover frequency occurs, which is at 3.6, and we have a phase margin of 65.5. That's in the open loop. That was just with putting this 1 over s times s plus 1 in a closed loop feedback configuration without a controller, but it's stable if we put it in a closed loop setting. The next time I see you might be the final exam. It will be in this room. Good luck with the rest of your finals. I've enjoyed this semester. We'll see you in about a week, less than a week.